Okay, can everybody hear me?
Yes.
Yeah. All right, so today we're going to continue. We're going to talk a bit about Logits, and then we're going to talk about optimization. The optimization stuff will be the most mathematical we do. In one sense, you don't need to, you're not going to need to remember it, but so many things can go wrong when you're doing a generalized linear model, a nonlinear model, that unless you've kind of been taken through the steps that are required in a numerical optimization, you will have no idea how to fix things. And so that's why we will go through this, and then you can refer back to it over time. Logits are used for lots of things. I've mentioned some of them. One of the examples we will use later on is how to do text analysis. So you use Logits, or you can use Logits, they're not the best things, to analyze text and to do translations and things like that. So that's surprising to people. They're really, they are for classification the workhorse that linear regression is for a regression. So the Logit Transform, so this is from last time. We had the P divided by 1 minus P equaled EXP X beta. Take the logs of both sides. And what you get is a linear function. So you have the log of this thing is a linear function of the x's. Remember, what we're trying to do is we're trying to explain this model. So what is P divided by 1 minus P? Well, that's the odds of y equals 1 over y equals 0. So 2 to 1 odds, 3 to 1 odds. So, you know, if it's 10 to 1 odds that you're going to have a 1, that's pretty likely you're going to have a 1. Okay. If it's 10 to 1 odds you're going to have a 0, it's pretty likely you're going to have a 0. If it's even odds, what does that mean? 50-50. It means that we really don't know. So interpreting the logistic regression model. What's going on here? We take the derivative with respect to x. Okay. So we have the log odds. So these are called the log odds, and this is called the Logit Transform. So the log odds is equal to x transpose beta. Okay. Take the derivative of that with respect to x, and we get our betas. And so what do our betas tell us? The betas tell us essentially, remember that the derivative of a log is a percent. Okay. So this is going to be the percentage change in the odds for a change in x. So that's a way to interpret this. Use of Logit, I mentioned, it's to predict. How do we do it? We simply use the Bayes classification rule. So I predict your probability of having a 1. If it's greater than 0.5, I say you're going to have a 1. If it's less than 0.5, I say you're going to have a 0. person with characteristics X is assigned to the class with the highest estimated probability. So if the probability y equals 1 is greater than 0.5, goes to class 1. If it's, let's say it's 0.4, that means that the probability y equals 0 is 0.6, and you would get assigned to a 0. So the beta is the change in the, and that should be the percentage change in the odds, okay, for a change in X. Now, some people are good about thinking about odds and some people aren't. It will behoove you to learn how to think about odds and what it means for a 1% change in the odds and a 10% change in the odds. You will find that the medical people, the biotech people, are very good at interpreting these things. Economists need to become better so at it. Okay? In general, a positive beta leads to positive increases in the probability that y equals 1 for positive changes in X. Let's see, I've got to move something here. Actually, I'd like you guys to vote on this. Do I need to talk about partial derivatives? So if I don't need to talk about partial derivatives, don't put your hand up. If I do need to talk about partial derivatives, put your hand up. And Herbert, can you take a count?
Sure.
So what I want to know is do I need to stop and talk about partial derivatives?
So I only see one person who is voting to.
Okay, so what I will ask then is that person make an appointment with me or with you, and we'll just go quickly through what partial derivatives are. I don't want to have to stop and do that if I don't have to. So I assume you all know what a derivative is. Hope you know what a partial derivative is. You have a function of 3 variables, then this symbol simply means to take the derivative of f with respect to x2 holding everything else constant. Now, what I do need to talk about is the gradient vector. So here's the partial derivative with respect to x1, x2, x3, and we put them into a vector, and that is called the gradient. And the gradient is going to be incredibly important in this class when we talk about optimization. The gradient is often written in many different ways. This is gradient of f. It's a p/1 vector. Okay. Sometimes if f, let's say f depends upon a vector x and a vector z, you will write partial x f, and that means we hold all of the y's constant, and then we take the partial derivative with respect to x1, x2, x3, x4. Sometimes we write it this way. We write down a typical partial derivative, and we enclose it in braces, and that means take the vector that's going to be partial f with respect to x1, partial f with respect to x2, and so on down to partial f with respect to x3. And sometimes they write partials as f sub I. I won't do that because we're primarily using subscripts in this class to indicate observations. It won't always be the case, but it will be mostly the case. I want to give you an example of somebody's waiting. Of what a gradient is. So here I have an ellipse or an elliptically shaped thing, and these are the level curves. Okay, so think of that this as a mountain, and these are the altitudes. Alternatively, you could look at this part of it, and they're in difference curves or production, ISO production. And what I'm going to do is I'm going to take a point y0 and a point x0, and that red line is supposed to be tangent to the level curve at x0 and y0. Okay. And now I take the normal to that tangent line. And what I mean by that is a right angle there. And the gradient direction is normal to the tangent line. So what the gradient is going to be a vector going in this direction of a certain length. And what's really important for us is just the direction of the gradient. I want to talk about convex sets. Okay, it turns out that we will rely on convexity and convex sets, and oftentimes when you use the methods we're talking about and they fail, it will turn out to be because of a lack of convexity. Okay, so I have a set of vectors in Rk, so that means each vector is length k. A convex set of vectors is a set where any average of two vectors is in the set. Okay, so if theta1 and theta2 are in the set theta, and I have a lambda between 0 and 1, okay, and if it is the case that lambda theta1 plus 1 minus lambda theta2, that is an average. That is an average of those two vectors. Okay. This should apply that the average vector is in theta. Then theta is a convex set. So I got the things backwards here. I'll fix that I'll fix that again. Okay. So here's an illustration. Here's a set that's convex. You take any line segment between any 2 points, and everything along that line segment is in the set. That's a convex set. Over here, we have a non-convex set. I can take a point here and a point down here, and anything in there is in the set. But if I take this point and this point and go along the line, there's a bunch of stuff here that isn't in the set, so this is not a convex set. Convex functions. Okay. So if theta is a convex set, and if f takes theta into R, so let's say f is a function of 2 variables, and it maps things into R, then f is said to be convex if, for any lambda, the following is true. Okay, and I'll give an illustration of this later on. But here I have the average of theta 1 and theta 2. Okay. And what do I have here? I have the average of f theta 1 and f theta 2. So this is f of the average, and this is less than or equal to the average of the f's. So the function of the average is less than the average of the function values. Okay. So let's see. I hope this works. Wait a second. Let's go back here. I was worried about this. Okay, I had worked out here a this was a video, and it's supposed to be running, and it isn't. Let me just check something here. Rats. Okay, so let's see if I can do this by hand. So this is, we'll call this x1. We'll call this x2. And this point here, we can write that as lambda x1 plus 1 minus lambda x2 for some lambda. So an average of x1 and x2 are going to be between x1 and x2. Now, here is f of x1. Here is f of x2. And here this is lambda f of x1 plus 1 minus lambda f of x2. Okay, so this is the average. This point is the average of these 2 points. And let's say, what is the value of f at the average? Well, that's right here. Okay, and this is definitely less than this. And so that's an illustration of what a convex function is. Concave functions go the opposite way. Let's see. Oh, criminy. There, look at that. Let's try it. Okay, so it would have worked. Well, I'll know better next time. With 2 variables, a convex function looks like a bowl, like this. Okay, and it's hard to visualize these things more than 2 dimensions, and so you have to go back to the definition of the function of the average is less than the average of the functions. So the generic machine learning minimization problem, and by the way, I say minimization here. Remember, we want to do maximum likelihood. You convert a maximization problem to a minimization problem simply by taking the negative of the objective function of the thing you're trying to maximize. So I think there are very few computer programs that do maximization. And so if you look for one, you wouldn't find it. And that's because everyone says, well, just negate the objective function and use a minimization function. Okay, so we want to do maximum likelihood estimation or minimum negative likelihood optimization. Okay, and here's the generic problem. We have n observations. We have a convex set, which will be our unknown parameters. We have a parameter vector in that set. In our case, forget about our case because I took that example out. We'll have a convex function of the thetas that depend upon the number of that depend on the observations. Okay, so in our case, it's going to be minus the log likelihood of we'll say z given the xn's and our thetas. Negation converts maximization to a minimization. And then we sum over the observations. That is, we take f theta is the sum n equals 1 through n of the log likelihoods. We're interested in two things. We're interested in the argmin of f theta. That is, we're interested in the theta that minimizes that, and that will be called the maximum likelihood estimator. And we're going to be interested in the minimum itself. That is, once we get theta hat, we take it and plug it into f, and that gives us the minimum value of the log likelihood, of the negative log likelihood. You have to remember when you work with minimization functions and you minimize the negative likelihood, when you work with the likelihood afterwards, you always have to multiply by a -1, or you will have really bad problems. Solutions. Under the assumptions that I had, only those assumptions above, it turns out the maximum likelihood estimator exists and is unique. Okay. You might want to check this. You don't have to. But the reason you want to do this is if you have a problem and you don't check to see whether the maximum likelihood estimate exists and is unique, you may be looking for something that doesn't exist. So you'll start your maximum likelihood program and it won't ever converge. It won't give you an answer. And the problem might not be that you used the wrong algorithm. The problem might be that you have posed a solution that doesn't exist or isn't unique. You run into this in a regression only in one situation, and that's when you have multicollinearity. So you have multicollinearity, and it turns out the ordinary least squares estimator doesn't exist or isn't unique. But you can check for multicollinearity very easily, okay? You can't, the only thing you can check for with these optimization problems is you have to check for the convexity. It won't be obvious whether things are convex or not unless you actually work it out. Okay. By the way, how do you find the solution? How do you find the likelihood solution? How do you find the thing that maximizes that? We did that by hand, but as I pointed out, analytically, we can almost never do that except in theoretical analyses. But we're going to need some facts from the analytic approach to motivate what's going on. Numerically is what we're going to concentrate on. So we're going to talk about the analytic stuff. I'll give you the framework so that we can understand what goes on numerically. So that's the reason for doing this, not so that you remember it, but so that you have in your mind what's going on. Okay. The analytic characterization is required to know if what you're looking for actually exists. So, analytic unconstrained optimization. So let's say you know that theta hat is in the interior of theta. Okay. You know that F is convex and twice differentiable, okay? You don't need twice differentiability, you simply need convexity. By the way, if the function is globally twice differentiable, then it is convex. Well, and the sign doesn't change. Hang on, never mind. I'll come back to that later. Okay, so the optimum is the solution of this. Take the gradient of F, set it equal to 0, and solve for theta hat. Okay, that is what theta hat is. Take the gradient, find the theta hat that sets the gradient equal to 0, to the 0 vector. Okay. I'm not going to spend a lot of time on the matrix of second partials. You should probably read about that. But oftentimes you'll get an error that says your Hessian is singular. And we can talk about that later on, but I at least want to point this out. So the Hessian is the matrix of second partials. So you take the partial with respect to one variable, the partial with respect to the second variable. And this is supposed to be positive semi-definite. What does that mean? Well, that's a matrix version of saying it's not negative. For those of you who've taken a linear algebra course, it means all the eigenvalues are greater than or equal to 0. Constrained optimization, theta hat is known to be on the boundary, and you've seen this in different contexts. Anytime you look at isoquants and isocost lines, and you ask what's the minimum cost point, and you have the isocost tangent to the isoquant, what you just did was a constrained optimization. So, you know, the boundary is the isoquant fixed at some value y, and you want to know what is the minimum cost with prices for producing that, and what are the inputs. So you've done this in the past. Again, F is convex and twice differentiable. Okay, and the constraint set is such that each component is convex. Okay, So the constraint set is convex. The point here is the solution to the constrained minimum exists and is equal to the solution to a certain saddle point problem I won't go into here. The key thing that's important is if you have a constrained optimization and your F is convex and your constraint set is convex, then you necessarily are going to have a unique answer. I'm going to skip over the part here on Lagrangian multipliers. I can come back if somebody wants me to talk about them later on. So we're going to talk about numerical optimization in the smooth case. Okay. Almost all algorithms can be cast into the following framework. Okay. There is a starting value. So this is the first thing that you're going to have to tell any algorithm. You're going to have to tell it, what the starting value is. Now, sometimes they will pick one by default, like 0. But what you want to do is you want to pick a starting value that's as close as you can figure intuitively to the correct value. I'll tell you where there's a problem. What if none of your thetas empirically can be 0? Well, if the computer starts at 0, you're going to fail. So you have to choose this, and you have to tell the computer what your starting value is. Then there is an updating rule of the following form. Okay, so you're going to start with a theta 0. P is going to be a direction, so it's going to be a vector. So this might be a 2 vector, this is a 2 vector, and alpha is going to be a constant. Okay, so what this says is we're going to start at theta I minus 1. We're going to go in the direction pi. We're going to go a distance alpha, and that's going to be our new theta. And then we're going to update I, and we're going to repeat this again and again and again and again. And I'll give you a visual of this in a minute. Okay. Alpha is called the step size or the learning rate. And it looks like it's not all that important. It turns out it's just absolutely crucially important. PI is the direction of search. And I'll skip over what the constrained rule says. Okay. And then there is a rule that tells you when to stop iterating. And the devil is in the details of that. Okay. In the unconstrained case, the methods are identified by the formulas for the alphas and the p's. We'll talk about gradient methods. Gradient methods have to do with the p's. We will have also, they're called batch methods. We'll have coordinate descent, which we'll use an awful lot, although it's very, very slow. But it always gets you the right gets you an answer if one exists. And steepest descent, which can be much faster, but oftentimes you will get things that don't converge. They don't stop. They just keep going and going and going, and you go, what the heck's going on here? Something called Newton-Raphson, which is a method which is a little bit like steepest descent, but it will go even faster. It will go really fast, provided you're close enough, but it too can get stuck. And these are all called batch methods for a reason, and that's because they'll work on all of the data at the same time. There's things called Quasi Newton methods, which kind of try to split the difference between the steepest descent and the Newton-Raphson methods. And these are called Fletcher-Powell-Davidon, Broyden-Fletcher-Goldfarb, and Shanno, and limited memory, Broyden-Fletcher-Goldfarb, and Shanno. And this is the one you want to use if you're using Quasi Newton. Then there are online methods. So these are not batch methods. Stochastic gradient descent. We will use stochastic gradient descent when we do neural networks. With neural networks, you cannot handle all the data and everything at the same time, and it's just easier to use stochastic gradient descent. Mini-batch stochastic gradient descent, which is where instead of operating as each observation comes in, you'll take groups of observations and bring them in, but you won't work on all of the data at once. So, what is the basic logic of optimization? And I want you to think about how you would reach the bottom of a valley blindfolded, okay? So, in fact, let's make it the bottom of a bowl blindfolded. You're up at the top, you have your blindfold, you don't know which way to walk. So let's say you walk one direction and you start going up, okay? Well, you know that the valley is bowl-shaped, so you know that's the wrong way to go. You can walk one way or the other way, but if you're not going down, you say, well, you know, I don't know. Say, well, maybe this is what I want to do. Maybe what I want to do is I want to find which way, while I'm blindfolded, it looks the steepest, and I'll just start walking that direction until I start going up again. Okay? So, we repeat this. We pick a direction going down. For example, the direction of the gradient. We walk in that direction until you start going up. Okay? That's referred to as the line search. That's, in essence, what you're deciding there when you walk in that direction and you start going up. That tells you what the alpha is. That tells you how far in the direction you walked before you stop. Okay. How far you walk is the step size of the learning rate. And you keep doing that until there are no downward directions. So you're at that first point and you go and you say, okay, I'm going up. Now I turn around and by stepping, figure out which is the direction going down. And I go that direction until I start going up again. And you have another step size or learning rate. And you keep doing that until no matter which way you walk, you be going up. And you say, okay, I found the bottom of the bowl. Now, let's see if I can make this work this time. Let's get rid of that. No. Run. Ah, there we go. Okay. Okay, so this is going to be your starting value. Okay, so you're going to have to tell the computer where to start. I'm going to call that y0 and x0. There's the tangent line. There's the direction of the gradient. And so you're going to start here and you're going to walk along the gradient until you get right here. Why is that? Well, you're going down, 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 down. And when you hit here, you're going to start going up, 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 up. And so you want to stop right there. Okay. And I'm going to call this x1, y1. Okay. So I was at x0, x0, y0. Now I'm at x1, y1. And I've just done one iteration. Okay. So now I repeat. Okay. That's supposed to be a tangent. I go in the direction of the new gradient. And I go down, 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 down until I hit where I'm tangent to a, what do I want to call it? A contour. And I stop there. And then I take another derivative, gradient, and I'm not even going to put the tangent line in there, but you can see what I'm doing. I'm going from here to here, and then I go along this line, and look how close I am to the final. So we call that the thick point theorem. Between any line and a point that are supposed to be tangent, there is a point thick enough that they are tangent. Whoops, let's go back. Go back. There it is. And I'll just jump to the end here. Okay. And so I'm right at the end, and I have my X star and my Y star, and I basically stop at that point. And the problem is, on a computer, how do I know I've gotten there? What if I move, 10 to the minus 15th one direction and 10 to the minus 13th another direction, and I go down a little bit? Do I keep doing that? If the answer is a real number, I can never represent that on a computer. At what point do I stop? I could look at the gradient. It should be at the minimum point. The gradient is equal to 0. Okay. Again, is 10 to the minus 13th small enough for each component of the gradient? And that's really going to depend upon the problem. That's really going to depend upon the units and that sort of thing. You know, the basic ideas of numerical optimization are really simple, but like I said, the devil is in the details, and there are a huge number of details. Line search. Okay, so we were moving in the direction of the gradient until we started going up. We'll try telling that to a computer. Computer's not going to have any idea what you're talking about. And so what we do is the following, okay, and we can do this. We say, okay, we have our theta. So this is where we are right now. Maybe this is theta I. We have our direction, the direction of the gradient, or this is the gradient. Okay. And then we have how far we're going to go along until we stop. And what we're going to do is we're going to minimize this. We're going to fix this, and I'm going to say, take the alpha that minimizes f in the direction p starting at theta. So I want that alpha, okay? This minimization can be done all sorts of ways. You could do it by taking derivative and setting it equal to 0. There are, as I said, all sorts of ways of doing that. That's called the line search. Oftentimes, what will happen is the computer will say, you had a line search failure. And that means the algorithm it was using for this didn't work. Maybe you ended up in a flat spot. Even though you're convex, you're nonetheless in too flat a spot, and you don't get anywhere. There's not an optimum. The other thing is, it turns out it doesn't matter a whole lot if you get alpha right. Okay, you just want to go in the direction p and not overshoot too much. Undershooting a little bit's okay. Overshooting a bit is okay. So you don't want to spend a lot of time doing the line search. If you get a line search failure, my advice to you is you just look into the controls, and it's going to tell you what the default line search is. Try each one of the other line searches. Okay. There really isn't a theory for why these things are going to work or fail. After the fact, you can look and say, ah, I see why it failed. But usually, in advance, the only way you could know that is if you knew what the answer was. And if you knew what the answer was, you wouldn't need to do the minimization at all. Okay. So this is the same as a univariate minimization problem in alpha. You fix theta, you fix the direction, and oftentimes, instead of solving a problem by taking a derivative, you'll take steps. So you'll go 1 step, 2 steps, 3 steps, and you keep doing it until you go up. And when you go up, it turns out you're guaranteed you've straddled the minimum. So you have a few points before you get to the minimum, and one point after you've got the minimum, and then you can use something called the golden search rule to find the minimum. Okay. The other thing you can do is you can do a polynomial approximation. What do I mean by that? You fit a polynomial to those points, and you take the minimum of that polynomial. That's easy to do, and you use that as your learning rate or your step size. You usually take a cubic approximation of the minimum along a line. Okay? Use the minimum of that polynomial as an approximation to the minimum. Remember what I said, it isn't essential that you get the step size exactly right. It's just you want to be always going down or close to going down. Okay? So it's not important to get the precise minimum. Steepest descent. One useful direction is the one that goes up or down fastest. Okay. And this is by given by the gradient at a point going in the correct direction. So you have the gradient and you want to be going down. Okay. The steepest ascent algorithm is this. You give a starting value. Let's say we have a starting value. Green this time. So I would be equal to 0, or I would be equal to 1. And so theta 0 is your starting value. You have the gradient at theta 0. And so one of the things you're going to have to do is you're going to have a program that writes that gradient. Okay. In the old days, you always had to program the gradients yourself. Nowadays, for most of the things you're going to be working for, the gradients are all done. So we're going to go in this direction, and we're going to go a step of alpha I, where alpha I is determined by a line search. Okay, we're going to get our new theta I, and then we're going to do it again, and we do it until we stop. The Newton-Raphson method, I'm going to, do I want to do this? No, I don't want to do this. I'm going to skip this. So what the Newton-Raphson method does, I'll just tell you what it does. It takes a quadratic approximation to the mountain at the starting point. So that the mountain is tangent to the quadratic surface. And then you find the minimum of the quadratic surface. I guess it shouldn't be the bowl. And you find the minimum of the quadratic bowl. And you take that as your approximate minimum. And then you, again, approximate the bowl again by another quadratic. And you keep doing that until eventually the quadratic and the bowl have the same value at the minimum, and then you're done. And it turns out the quadratic you use requires that you know the matrix of second derivatives of the likelihood function, or the log likelihood function. The matrix of second derivatives, first, is very hard to program. Second, it often turns out to be singular, which is very much like collinearity. And when that happens, you'll get stuck. Sometimes you get stuck in a circle and go around and around and around and around. Sometimes you just get stuck between 2 points and bounce back and forth, back and forth, back and forth. The other thing is that Newton-Raphson doesn't do very well if you start far away from the true minimum. It doesn't do a good job at all. So Newton-Raphson is guaranteed good only close to the minimum, and this matrix of second derivatives is very hard to calculate. Okay, the inverses are very hard, and that's usually where the thing breaks down. So the thing isn't truly singular, but it is numerically close to being singular, and it just messes everything up. Okay. I'll just mention in some old programs where, in fact, even some not so old programs, I have found when they failed, it's because somebody miscoded the matrix of second partials. And just think about this. Let's say you have 500 thetas. That's 500 times 499 over 2 second derivatives you have to take. And what's the possibility you don't make a coding error on at least one of those? It's probably pretty small. And that might be singular for some iterations and not for others. So Newton-Raphson is nice theoretically. If you know you're close, go ahead and use it. You usually want to make sure that's not the default. Fletcher-Powell-Davidon, I mention it only for historical reasons. What they did is they were the first ones to say, hey, let's just approximate the matrix of second partials in some fashion. And they would approximate the matrix of second partials. Now, the reason for mentioning this at all is the following. It turns out that matrix of second partials is very, very closely related to the variance estimate for your parameters. And so even if your likelihood converged, so you got good estimates, it turns out that this approximation often doesn't converge. And so if you assumed you had the matrix of second partials, your variances would be incorrect. And so one of the problems that you have to worry about when you use these methods is that the matrix of second partials in fact converge. Or what a lot of us do is we get our estimates and then we use those as starting values in a Newton-Raphson and just take one step with the Newton-Raphson. Okay. The Fletcher-Powell-Davidon was superseded by the Broyden-Fletcher-Goldfarb and Shanno. The BFGS, you don't need the details of this, but it does two things. It doesn't approximate the matrix of second partials. It approximates the inverse of the matrix of second partials so that you don't have to take an inverse. It does still have the same problem that you don't necessarily converge to the true matrix of second partials, but it's pretty good. And I'll just go through that. You don't need to look at that. Online learning. Okay. So far we haven't used any of the structure of the data whatsoever. We just, kind of do it all at once. And here's why we might need it. Okay. The data set is too big for any computer. So we can't get the data into a computer. It's called online learning because oftentimes you'll have something like this. You will have people interacting with Netflix. Okay? And every time they choose a movie or don't choose a movie, you have a new observation. Well, you don't want to have to go and redo the whole Newton-Raphson or whatever you're doing every time one new piece of data comes in. On the same token, you don't want to ignore that data either, or those data either. Turns out some methods aren't parallelizable. And so if you can't get the data set into the computer, you're really kind of dead. You can't even do the optimization at all. Okay. So I say, pick your reason. There's so many reasons for these things to fail. Okay. Getting tenure at a good place, for example. Anyway, getting a job at a good place. Keeping a job at a good place. So, large data sets. So far, we're talking about batch optimization with all of the data in memory at the same time. That's what batch optimization means. Okay. Either it's parallelizable or it fits in one computer platform. Okay. I have an early solution. We don't need to go through that. Okay. Stochastic gradient descent. So what we're going to do here is we're going to update as observations come in. Okay. Oftentimes you'll hear about Kalman filters and you go, what is going on here? Really updating a linear model as observations come in. So think about, you have a large regression, you've calculated, you've done ordinary least squares, you did LM, it took 20 minutes to do it, a new observation comes in. Do you want to have to redo your whole estimation? It turns out you don't have to. It turns out there are updating formulas that will allow you to update observation by observation. For the linear model, it's called a Kalman filter. And I just say that for context because you'll see that oftentimes in papers you read. They'll say, yeah, in the linear model, we did the Kalman filter. And you go, what are they doing? All they're doing is updating observation by observation a linear model. Otherwise, this is what we do. Okay. We initialize theta and alpha. That is, we have a starting value and a starting learning rate. Okay, and then we repeat the following. We randomly permute our data. Okay. For I equals 1 through n, we do this. Okay. We take the gradient at the current theta as the current gradient. Okay, that's fine. Okay, I forget about that. And we update AN. And we do that till we converge. And you may go through the data many, 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 many times. Those are called epochs. The nice thing about this is you don't need your data all in there at the same time. Mini batch stochastic gradient descent, you take data in groups of n, initialize, and repeat again. Okay. Learning rates, this is key. Okay. You need some sort of one-dimensional minimization in the search direction. I mentioned that before. Direct search, that means you just basically are going along until you move up, start going up. The problem with that is it can take a long time. There's something called golden rule bisection, which says that there's actually optimal step sizes you can take to find a minimum. You can do a cubic approximation of this in the direction P. Stochastic learning rates, I'm not going to cover this. Stopping. So the last thing we have to know how to do is stop. And we're going to use primarily non-stochastic optimization. We're going to stop when some combination of the change in the minimum, the change in the minimizer, and the norm of the gradient becomes small. So sometimes you'll sit there and say, if theta hat isn't changing, then we're done. Sometimes you'll say if the gradient isn't if the gradient is 0, that is the norm of a 0 vector is 0. So if that gets really small, you say, okay, we are essentially at 0. Or if you say, see the minimand isn't changing, or if you're maximizing, if the log likelihood isn't changing, you say, okay, we'll stop then. Most of the rules are a combination of those, some average of those three. And if all of those changes are small, then you stop. Part of the problem there is a problem of units. You start changing units, and what had you stopped before now won't have you stop. So I'll give you an example. If you're doing things in terms of pennies, and you know, you're stopped when you're within a penny, you know, that's great. If you're doing things in dollars and you stop within when you're within $1, that's fine if you're looking at GDP or looking at somebody with $100 or $200. But if you're looking at somebody who has only $1 or maybe $2, being off by $1 is an awful lot, and you would want to work in pennies instead of dollars. We'll talk about stochastic optimization later on when we talk about neural nets. Those are the references. So I went through this way faster than I thought I was going to. I guess we can ask some questions. Any questions? Okay. Sure. Sure. Let's go even further back than that. So convex sets, okay? So you have a set, and the point is that the average of any two vectors is in the set. So you have a set, take two vectors out of that set, and form their average. And you ask, is that average in the set? Now, what's an average? Okay, so I have a, let's see if I can do it this way. I might have a, let's go back. So I might have a, I'll say a y1 x1 and I have a y2 x2, okay? And these are two vectors in the set, okay? So this vector and this vector are in theta. And now I'm going to take the average, okay? So let's say I make it 0.3 plus, and this is going to be 0.7. And so what that means is I'm going to get a new vector, and that new vector is going to be 0.3 y1 plus 0.7 y2 as its first component, and its second component is going to be 0.3 x1 plus 0.7 x2. And the question is that going to be in theta as well? If the answer is no, then theta is not convex. If it's yes, then we have to go through every single possible theta from, or lambda, from lambda equals 0 to lambda equals 1. And we have to do that for every single pair of vectors in theta. And if it is the case that for every single lambda from 0 to 1, and every single pair of vectors that are in theta, that the average defined in this way is also in theta, then theta is a convex set. And the illustration was this way. So we could treat this as theta 1, this is theta 2, and anything along here is an average of those two. So we'll call this x, we'll call this y, and this would be maybe y1. This is, whoops, whatever. Erase that. I am learning how to use this thing. X1. Okay. And here is X2. Here is y2, and any point along here is going to be the same average of y1 and y2 as for x1 and x2, okay? So if this is x1 lambda plus 1 minus lambda x2, that is, let's say the lambda gives us that point, then this point is going to, with the same lambda, be y1 lambda plus 1 minus lambda y2. If I move to a point here, it means that the lambda has changed. If lambda is equal to 1, I get this point. If lambda is equal to 0, I get this point. And so everything along this line is in this blue set. And I can't pick any 2 points and any lambda for which that's not the case. In contrast, over here, I have this point, and here's something on the line in between them that is an average, and you'll note it's outside the set. So this is not a convex set because it doesn't satisfy the case that for all points. So here's a point, here's a point, there's a line. For that line and those points, it works. And in fact, it works for a whole bunch of points, but when I come over up here, it doesn't because of this indentation. And so that makes the set non-convex. Did that answer the question about convex sets? Okay. So this has to be true for all possible lambdas. So it has to be true for all possible lambdas. Now, there are ways of proving sets are convex, but by and large, what you do is you assume they're convex, you make them convex by construction. So for example, a square is convex. You cannot pick any pair of vectors in a square and put a line between them and have that line go outside the square. Similarly, a circle is convex. And so oftentimes you'll sit there and you'll say, I'm just going to choose my set so that it is convex. And oftentimes there's no reason to do otherwise. What you can do, though, is sometimes, you know, economic theory might tell you that a set is not convex, one that you wanted to use, in fact, and then you're not going to be able to necessarily use these methods. Now, as it turns out, these methods can be adjusted to handle non-convex functions as well as non-convex sets, but you have no guarantee of uniqueness, you have no guarantee of existence. So oftentimes you can show that a set is not convex. It's very hard to prove that an arbitrary set is convex. You will learn how to do that if you take an advanced real analysis course, but those will turn out to be hard homework problems. really hard homework problems.
I have a follow-up to that.
Okay.
If you're using just an arbitrary set, an arbitrary convex set, how are you guaranteed to find a norm for that, or a normal? Like, how do you choose your starting point so that they meet at a point that's
now let's be careful here. So the convex set. So you're confusing the convex function with the convex set. So let me jump ahead here. Okay, so here would be an example where there is a convex function, okay? The convex set it's defined on is this rectangle. So the rectangle might be, this might be theta 1, this might be theta 2, and then the this might be f of theta 1 and theta 2. Okay, so this function is convex. Okay, the parameter set is convex. So here the parameter set is convex. Now, I could have made this a circular set as well, and that would be convex. Okay. Where I would have a problem is imagine that my set looks something like this, and what I'm doing there is I'm basically decomposing or splitting this rectangle down here. And let's say the only part of the parameter set is this part in here. Okay. It may turn out to be the case you can't find a unique optimum in that case, even though the function is convex, because the set it's defined on is not convex. That can be the case. The bigger problem is usually the non-convexity of the function itself. So here's what's the problem with a non-convex function. Just draw this over here. So let's let this be x. Let's let this be f of x. And here is a non-convex function, okay? And the problem you can run into here is you do your find the bottom of the valley, and you started here, and you're going to go right here. The problem is the real optimum is over here. And so what you found was a local optimum, and you can't guarantee just by looking around there and saying, look, I'm at the bottom of a bowl, that there isn't a bowl over on the other side of the mountain that's even deeper. And so that's why you need convex functions. That can't happen in this case. That is, if you know the function's convex, then it only has one optimum, and it's right there. So separate the convexity of the parameter space, which usually is not a problem. That is, we usually don't have a theory that tells us that the parameter space has to have a weird shape. Usually we'll take the parameter space to be either all of Rn or Rp, or all of RP for some variables and positive R for other variables. So we might take the positive orphant of RP, but all of those will be convex. Sometimes if we're working with, and we won't do this, well, I guess we will in two cases. When we work with polar coordinates, when you're working with angles and I'll think of it in a second, radii, the radii will go from 0 to infinity, can't be negative, and the angles will go from 0 to 2 pi. Again, that parameter space is going to be convex. The functions might not be. So a sine function is not a convex function, even though it's defined on the real line, and the real line is a convex set. So does that make sense?
Yeah, it's starting to. Thanks.
Other questions? So when we come back next time, I'm going to go fairly deeply into Logit models, and I'll be doing it mostly by modeling. Herbert, are you going to cover GL tonight?
Yeah, I'm going to cover GLM today.
Okay, so you'll learn the GLM program. And the GLM program, one of the things that we'll do is a logistic regression. And we'll spend a fair amount of time working with that, seeing how it will work. I'll talk to you about some applications where you would use Logit models, and we'll talk about how you would put them together. So you're writing a thesis on something. Okay, what's going to go into this and why. Then we will talk about what's called linear discriminant analysis, and we will talk about again. We'll talk about k nearest neighbor classification, but with the idea there of comparing the methods. So we're going to have 3 methods for doing classification. We're going to have logistic regression. We're going to have a linear, and actually I'll probably do quadratic discriminant analysis as well. And then we've already talked about KNN, and we're going to ask the question, how do these compare? That's in the classification chapter in ISLR, the Introduction to Statistical Learning with Applications in R. I think it's chapter 4. I'm assuming that chapter 3 is what you did in 482, and so if the regression stuff isn't making sense to you, read chapter 3 of ILSR. And then I want you to read the chapter in Matt Taddy's book, if you have that book, that covers the same materials, basically covering the GLM. Now, in his case, he kind of mixes the regression and the generalized regression together, but it can't hurt to read that. And then I'll talk more generally about the generalized linear models, and we'll talk about the other kinds of data that generalized linear models handle. So right now we have a linear model, which is certainly a generalized linear model, and that handles regression data where the dependent variable is continuous and cardinal. We have logistic regression, binary logistic regression, that handles classification. I will talk about what's called the multinomial logit, which is something that economists invented, a guy named Dan McFadden. It's one of my thesis advisors, and he got a Nobel Prize for it, which gives an economic context for what are called multi-class classification problems. And the multi-class problems are used quite a bit in economics, not so much in machine learning. Then there are things that are called count data. An example of count data are so-called Poisson models. So how many errors were there in orders at Amazon last week? It could be 0, it could be 1, it could be 2, it could be 3, it could be 4. And turns out that's not modeled really well with a linear regression. What it is modeled well with is what's called a Poisson regression for count data. And we'll talk about those models. And then we'll talk about over-dispersed Poisson models. And so that's a situation that you see quite often. You have count data, 1, 2, 3, 4, etc. But 0 is quite special in that almost all the probability is 0. So, you know, what's the probability that somebody gets killed in a airplane crash? It's almost 0. It's almost 0. But you could have 1 person killed in a crash, 2, or you could have 1 crash, 2 crashes, 3 crashes. You just go by the number of crashes. And most of the time, there's not going to be a crash. Well, it turns out the Poisson doesn't model that very well, but there's something called a two-stage hurdle model, which falls into these generalized linear models that does a very good job. And so the point there is we're going to learn to look at data and say, this is a classification problem, so we should be using one of the classification models. This is a count data model, so we should be using one of the count data models. This is a standard regression, so we should use one of the regression models. I'm not going to cover them in this course, but there are also models for rank data, for things that are not cardinal, but also aren't labels. So to say I'm the tallest and she's the second tallest and he's the third tallest and she's the fourth tallest, those aren't simply labels. They actually tell you something. But like I said, you know, if you're the median height person, that does not mean you're half the height of the tallest person or infinitely taller than the smallest person, the 0 person. So that's what I'm going to talk about. That's what I'm going to talk about next time. And if you need to refresh on mathematics, just send me an email and we can talk about doing that. Eventually, I'm going to get this to the point where I have both the amount, the time that goes in the lecture, and the content of the lecture set up right. Right now, I still don't have this right because I'm still learning how to do this stuff online. Any other questions? Okay, that's all I have to say tonight, and I'm sorry that I didn't get further. Had I known I was going to go through faster, I would have done that. Okay, Herbert will take you through GLM later. Pardon me. Okay.